This wireframe animation shows a human figure in a mid-air jump. Notice how the glowing brain node pulses in sync with the physical exertion. To understand the mechanics of language acquisition, we have to look at how the body processes information. In early childhood second language acquisition, traditional desk-based pedagogies often create a cognitive bottleneck. Students struggle to comprehend basic expressions, which leads to stalled progress and low motivation. Static models frequently treat language as an isolated memory exercise. This approach lacks the emotional, spatial, and interactive context that turns abstract vocabulary into usable communication. This friction is most visible in vulnerable populations. Children with limited access to specialized educational resources often face the steepest barriers in these rigid, repetition-heavy environments. Researchers at the Relate Group, operating within the Uniminuto Futures of Education School, began analyzing this breakdown to find a better way forward. Their thesis posits that language learning is not a passive memory task, but an active, bodily experience that must be socially relevant to the learner. To test this, they launched Embodied English, a pedagogical project designed to map kinesthetic inputs directly to linguistic acquisition. The project's design suggests that for these demographics, moving L2 acquisition beyond the desk is the starting point for addressing the literacy gap. This approach relies on the theory of embodied cognition. The premise is that physical perception and bodily movement actively facilitate memory retention. This schematic demonstrates the biological mechanism. When receiving the command jump, the brain processes the text and fires an impulse down the spinal cord directly to the target muscles. This physical mapping reduces the cognitive load required to appropriate functional expressions in English. The team applied this framework to a cohort of 16 children from the Las Cruces neighborhood. To test the model's impact on groups facing severe educational resource constraints, the cohort included 10 girls from the Fundación Sagrada Familia. The curriculum is governed by Participatory Action Research, or PAR. This flowchart outlines the 4-step cycle: observation, reflection, action, and transformation. A central slider represents the constant need for context-sensitive adaptation. Instead of relying on standardized testing, PAR utilizes qualitative field journals and direct observation to evaluate progress and refine the sessions. This ensures the educational environment functions as a responsive feedback loop, adapting the pedagogy to the specific responses of the children. To execute this theory, the team developed the Brain-Body Virtual, or BBV, model. The first pillar, the brain station, focuses on conceptual recognition and vocabulary mapping. This environment is calibrated for comprehension. Students learn English instructions before moving into physical action. Once the vocabulary is understood, the focus shifts to the center pillar, the body station. Here, routines and commands like stretch, turn, and clap are used to lock in the vocabulary introduced in the brain station. This video shows the transition from processing to execution. By forcefully clapping in a precise rhythm, the child uses physical participation to reinforce the language. These choreographies also address disparate learning levels. Students who struggle with verbal instructions can use physical mirroring of their peers to stay engaged. The intersection of the brain and body stations bridges the gap between conceptually knowing a word and functionally using it in a real-world context. Returning to the BVV schematic, the third pillar is the virtual station, expanding into digital network nodes and VR interfaces. This station incorporates technological resources and virtual reality into the curriculum, scaling interaction and motivation through visual and auditory contexts a standard classroom cannot replicate. Immersive environments are especially useful for these cohorts, who often have very little real-world exposure to native English speakers. The virtual station acts as a scalability engine, allowing a localized physical classroom to connect with a wider digital linguistic landscape. This matrix tracks the 2026 update. Pedagogical achievements are in the green column, identified challenges in amber. Linguistic achievements include executing kinesthetic commands and functional phrases. Observations show strengthened associations between English vocabulary and bodily actions. Beyond linguistics, the PAR methodology also recorded socio-educational metrics during the observation phase. The project documented high attendance rates and clear respect for different learning rhythms among the participants. Additionally, the 10 girls from the Fundación Sagrada Familia demonstrated highly positive, active social integration with the broader participant group. These results suggest kinesthetic pedagogy simultaneously supports both linguistic competence and social inclusion. To maintain academic rigor, the 2026 update also identifies the logistical friction points encountered during implementation. This split screen shows primary constraints. On the left, hardware scarcity limits the virtual station. On the right, significant baseline skill disparities require constant curriculum adjustments. The researchers also noted difficulties in applying traditional diagnostic instruments to this specific population. This Venn diagram shows the project's structural conclusion. The 4 nodes, education, language, body, and technology, intersect to create the learning environment. This central intersection reflects the move away from isolated desk work, treating language acquisition as a coordinated experiential process. The findings suggest that for these children, acquiring English becomes a physical act of moving, interacting, and participating in a shared social environment.